So I'm Tom, and I'm excited to share with you my work about model-based real-time quantitative ultrasound and radar, which I did with Professor Ronina Eldar at Weizmann Institute. Quantitative medical imaging represents the physical properties of the scanned medium. It means that each pixel value has a physical interpretation. For example, we can recover the density map of the scanned medium using ultrasound signals, for example, and it means that each pixel value is the density value of the medium. This can be beneficial for the reverse medical application. For example, for fatty liver disease, when we want to know the fat percentage of the liver, or for fast stroke imaging, when we want to know the blood spread over time. And we are going to represent this scattering object as random oval. To achieve the images, we transmit a pulse which propagates over space and time and record the scattering signals from the object. We can calculate these scattering signals from unknown medium and physical properties using the wave propagation equations. This is known as the forward problem. We want to solve the inverse problem, meaning to recover back the physical properties mapping from the recorded signals. The inverse problem has no closed form solution, and we are going to use a neural network to recover multiple physical properties in real time. In our setup, each element or antenna transmits a pulse, and the rest record the signals, and so on. And we were able to accurately reconstruct the physical properties mapping using data from only 8 elements, compared to dozens or hundreds. And we use diverse transmission setup. For example, tomography, as you can see on the left, when the elements surround the object, or a linear probe, as you can see on the right, when the elements are only on one side of the object. This is a much more complex scenario, as we don't have information about the differences between absorption of the signal and a continuous propagation of it. There are known methods to recover the physical properties from the scattering signals. For example, the full waveform inversion, which is an iterative optimization method based on gradient descent. This method needs no training and can recover multiple physical properties. However, it's time-consuming and tends to converge to local minima and need initial guesses which are close to the true solution. The FWI loss consists from the differences between the real measured scattering signals, the tensor M, and the predicted one according to initial guesses of the physical properties, denoted as theta, and the wave propagation equations, denoted as the function f. We are going to use a neural network to recover the physical properties in real time. We use simulations as training set, and we use diverse training sets. For example, undefined object shapes based on the MNIST digits, or realistic brain slices with a random stroke based on MRI scans. We assign the physical properties values based on the medical condition we want to simulate, and use the wave propagation equations and the non-pulse and transmission setup to calculate the input receiving scattering signals, the tensor M, which is a three-dimensional tensor, consists for all the receiving channels, each element recording, dings, and C, for all the time samples, and T, for each pulse transmission, and P. We are going to use a model-based deep learning schemes, which combine in the network architecture or learning process a known model, for example, the wave propagation model. They are known to be better than a pure analytical solution, as they can overcome partial domain knowledge. This leads to better inference time and results. In addition, deep learning schemes known to be better in the literature than a standard neural network, as they need to learn only the really unknown part of the things that we want to solve, of the problem. The network doesn't need to learn from scratch everything. This leads to better generalization and requiring less data. This is our network called MBQRAS, which stands for Model-Based Quantitative Radar and Ultrasound. It uses unfolding of the FWI to learn the gradient using a unit block. The input of the network are the measured signals, the tensor M, and initial guesses similarly to the FWI, the optimization method. For example, average property of water. Then the network architecture is based on the wave propagation equations to output the reconstructed physical properties. And we can use the same architecture for different signals, for example, for radar signals. Here we can see an example of our architecture for the ultrasound signals. We use the initial guesses to calculate the predicted scattering signals, similarly to FWI. Then Then we input to the unit block only the differences between the measured signals and the predicted one. In this way, the network focuses the learning only on the part of the signals that are related to the really unknown objects. The output from the unit block are the tensor G, which represent the general descent directions related to these differences. We use some update steps to subtract from the initial guesses the tensor G and do a ReLU activation to get the reconstructed physical properties mapping. One of our novelties in our method is having a time representation of the scattering signals to have a spatial representation of it. It means that we're referring to the receiving channels and the time samples as a spatial domain, a spatial dimension in the convolution layers. You can see here example for the linear probe, for example. So the receiving signals dimension is actually the position of the element's axis, and this is perpendicular to the time samples, and both span the spatial image domain. This allows us to exploit symmetries in the receiving signals tensor, and to take advantage of conventional non-computer vision method in the signal domain. For example, we use straight convolution to learn from non-neighboring time samples and elements. To evaluate our result, we use diverse numeric matrices, for example, normalized RMSE, PSNR, transosmolarity, to evaluate the accuracy of the pixels themselves reconstruction, along with the position, shape, and size of the objects. Here you can see an example of our reconstruction for the ultrasound signals. We are able to reconstruct undefined object shapes based on MNIST digits with liver properties, noisy non-homogeneous medium, object with noisy input signals, and from different transmission setup, tomography, and the more complex one of linear probe. And our network was able to reconstruct 2 scattering objects, even when the training set consists from only 1 object in each example, demonstrating the generalization ability of the network. We achieve real-time results with less than a second, compared to FWI, which takes more than half an hour, and improved numeric matrices using data from only 8 elements. In addition, you can see different datasets that we used of realistic liver scan from CT scans of patients, using both tomography or linear probe, when we achieved improved results. For the radar case, we were able to reconstruct undefined scattering object shapes based on MNIST digits, and the realistic brain slices with a random stroke in it, with different orientation, even when the stroke was in the middle of the brain, when the skull caused a degradation in the signal quality. We achieved real-time result with lower normalized RMSE, higher PSNR, and structural similarity, using data from only 8 elements. Moreover, we evaluate our method on real recorded signals we did from a scan in our lab, using Verisonic machine. We scan a phantom using ultrasound scan, and we evaluate our result. In the bottom line, we can see the traditional B-mode ultrasound image when the objects are circled in red. And we achieved improved result. We were able to reconstruct the physical properties of the medium and the accurate position, size, and shape of it. Moreover, you can see on the right that our method was able to reconstruct 3 scattering objects, even in the training set that the training set consists from only 1 object in each example, which demonstrate the generalization ability of our method and promising capabilities. To conclude, we present a quantitative method to achieve real-time reconstruction of multiple physical properties that work on realistic and real recorded signals from different signals, ultrasound and radar, and diverse transmission setups, both tomography and the linear probe, using data from only 8 elements. Thank you.